In this video, we're going to go over the review sheet for circles quiz number 1. So in the first question, we're given two endpoints of the circle, and we need to write the equation of the circle. In order to write the equation of any circle, we need two things. We need the center and we need the radius, and here we don't have either of those. So first, we're going to find the center, and since we have two endpoints of the circle, the way that we're going to find the center of the circle, and we're told that A and B are actually endpoints of the diameter of the circle. That means that the line formed by A and B passes through the center of the circle. So the way that we're going to find the center of the circle is we're actually going to find what's exactly in between points A and point B. So you can do this graphically, but I want to make sure that I don't make any mistakes doing it. So I'm going to do this using the midpoint formula. So I'm going to take points A and B, and I'm going to plug into the midpoint formula, which is the average of the x coordinates, comma, the average of the y coordinates. So that would be -4 plus 4 over 2, and that would be 2 plus -4 over 2. Simplifying that real quick, that would be 0, -1. So 0, -1 is right over here, so that would be the center of the circle. The last thing that we need is the radius. So let me just graph this circle really quickly to make it look more circular. Now that I know what the center of the circle is, I can put my compass on the center of the circle, and I can use my compass to draw the circle. Okay, so that's almost exact over there. So in order to find the radius of the circle, what I need to find is I need to find the distance from the center of the circle to one of the endpoints. So we can do that using the distance formula. We are going to need to use the center of the circle, and we can use either of the two endpoints of the diameter to find the radius of the circle. So the distance formula, let me do that right over here. And let me write it down. Radical x2 minus x1 squared plus y2 minus y1 squared. Okay, let me plug in the center of the circle, and I'll just use endpoint B since I'm over here. Both about the same. So let me use for x2, 0, and then for x1, I will use 4. For y2, I'm going to use -1, and then for y1, I'm going to use -4. Okay, so that's -4 squared, that's 16. -1 minus -4, that's -1 plus 5, so that's 4 squared is 16. So we have radical 32 as our radius. So I'm going to write that here. The radius is radical 32. Okay, so now I am going to write the equation of my circle using the center and the radius. Oops, slight error over here. If you type into your calculator, -1 minus -4 squared, that is 9. So slight error there. Let me just change that. So then we would have 16 plus 9 under the radical, which is radical 25. And that gives us a radius of 5. There we go. Okay, so now we're going to write the equation of the circle. So to write the equation of the circle, plug into the formula x minus h squared plus y minus k squared is equal to r squared. H is the x coordinate of the center. K is the y coordinate of the center. So here, the x coordinate of my center is 0. So that's x minus 0 squared. You can just write x squared plus y minus the y coordinate of the center is -1. And our radius is 5. So in simplest form, that would be x squared plus y plus 1 squared is equal to 25. So that would be our final answer. That would be the equation of this circle. And let me change this here so this is not confusing anybody. That's 5. The radius was 5 of this circle, 5 units. And we can also see that graphically as well. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we could see graphically here that the radius is 5 as well. Okay, for number 2, we have somebody's work for changing a circle equation into standard form. And it appears that they were doing that by completing the square. And what we have to do is we have to figure out in what step the error was made. And the error here is in step number 2. Remember that when you're completing the square, whatever you add to the left side of the equation, you also need to add to the right side to keep it balanced. And in step number 2, Kevin added 4 to the left side of the equation, but instead of doing the same thing to the right side of the equation and adding 4, he actually subtracted 4. So step 2 is where the error was made. In number 3, we are actually going to complete the square so that we can take the equation of the circle and change it into standard form so that we could see what the center and the radius are clearly. So I'm just going to rewrite my equation right here. That's x squared plus y squared is equal to 8x minus 6y plus 39. First thing I want to do is group the x terms together, group the y terms together, and put the constant by itself on one side of the equal sign. So let me group the x terms together. So we have x squared, and then on the right side of the equal sign, there's an 8x. So if I move it over to the left, that will be a minus 8x. Then I see a y squared, and there's also a negative 6y on the right. If I move it over to the left to be with the other y term, that would be a positive 6y, and that is equal to 39 should still stay where it's at on the right side of the equal sign. So what I want to do now is find the term that completes the square for the x terms and the y terms, and whatever I add to the left side of the equal sign, I also need to add the same things to the right side of the equal sign to keep the equation balanced. So the way that we find what goes in the box is we do b over 2 squared. So for our x terms, here's our b coefficient, and for our y terms, here's our b coefficient. So negative 8 divided by 2, that's negative 4, squared is 16. So whatever I'm adding here, I'm also going to add here. There we go. And I'm just going to do 2 steps at once because we know that the step after this is to factor the x terms, and it's going to factor to the same factor repeated twice. And the way that we figure out what it factors to really easily is we just think about what b over 2 was before it was squared. So here b over 2, that was negative 8 over 2, that was minus 4. So 2 steps at once, that's already factored now. Okay, for the y terms, 6 over 2 is 3, squared is 9. So whatever I add to the left, I also have to add to the right. And then factoring here, it's going to factor to the same factor repeating twice. What goes in the parentheses is b over 2 before it was squared. So here that's 6 over 2. That is just positive 3. Okay, now I'm just going to add up all the stuff on the right side of the equal sign, and then we're all finished. So that's 39 plus 16 plus 9, and I got 64. So the center of this circle would be 4, negative 3. Remember, it's like the opposite signs because in the format for the equation of a circle, there's already a minus there. So if I'm seeing a minus 4, that means it started out as a plus 4. And if I'm seeing a plus 3, that means it started out as a minus 3 because the minus made the plus. And remember, what's on the right side of the equal sign is r squared. So regular r would be 8. The square root of 64 is 8. For number 4, it says if the circumference of a circle is 10 pi, what is the area of the circle? So I know that circumference is pi d. You could also use 2 pi r. And if the circumference is 10 pi, then I can actually solve for the diameter. And I can do that by dividing both sides by pi. If there's a pi in the top and the bottom, it cancels out. So I have that the diameter of the circle is 10. If the diameter of the circle is 10, that means the radius of the circle is half of that, which is 5. And area of a circle is pi r squared. So plugging in 5 for the radius, we have that area of the circle is 25 pi. That's answer choice number 2. For number 5, it says the diagram shows rectangle ABCD with diagonal BD, and we need to find the perimeter of rectangle ABCD. Well, I know that rectangles have 90-degree angles, so these two angles are 90 degrees. So if this is 30 and this is 90, this angle here has to be 60 degrees. So I'm seeing here that I have a 30, 60, 90 triangle. And we need to find the perimeter of the rectangle, so it's also important to keep in mind that opposite sides of a rectangle are congruent. That's a property of a parallelogram, so it also applies to a rectangle as well. So to find the sides, I know that in a 30, 60, 90 triangle, the sides are in the ratio 1 to radical 3 to 2. And we're given the biggest side here is 12 because it's across from the biggest angle, the 90-degree angle. So the shortest side is half of the biggest side. So that tells us that the shortest side across from the 30-degree angle should be 6. And to get from the shortest side to the middle biggest side, we multiply by radical 3. So the middle biggest side across from the 60-degree angle should be the shortest side times radical 3, or 6 radical 3. So now we can find the perimeter of the rectangle because opposite sides of the rectangle are congruent. So we can add 6 plus 6 plus 6 radical 3 plus 6 radical 3, and we get 12 plus 12 radical 3. That's our perimeter. That doesn't simplify any further. Oh, it says to the nearest tenth. I almost missed that. Let me put this into my calculator. So 12 plus 12 radical 3 is approximately 32.8 units. So the equivalent of that is approximately 32.8 units. In number 6, we have circle O, and we're given chords AD and chords BC that intersect at E. Remember, chords are just segments in a circle that don't pass through the center, just any segments that don't pass through the center. And it's asking us which relationship here must be true. So the first one is saying triangle CAE must be congruent to triangle DBE. Well, let's see if that's true. So we have a couple of inscribed angles here. I'm going to highlight some of them. So I see angle A here. Oops. Is an inscribed angle. And it's an inscribed angle because if I highlight it, notice how the vertex of this angle is on the circle. And I see that it's opening up to arc CD. Let me put that here in the diagram so that we can see it a bit better. I also see that angle B over here is also an inscribed angle. It has its vertex on the circle, and it's also opening up to the same arc CD. And remember, if we have inscribed angles that intercept the same arc or congruent arcs, that means those inscribed angles are congruent to each other. So we do know here that angle A and angle B should be congruent to each other. So let me mark that in the diagram. Angle A congruent to angle B. Let's see if there's anything else that we know here as well. I see more inscribed angles. Let's see if we can figure out anything about them. So angle C here is an inscribed angle. Its vertex is on the circle, and it's opening up to arc AB. And I see also angle D is an inscribed angle with its vertex on the circle that's also opening up to the same arc AB. So once again, inscribed angles that intercept the same arc or congruent arcs are congruent. So we know that angle C and angle D are congruent to each other. So I'm going to mark that in the diagram so we can see that a bit clearer. Angle C congruent to angle D. And as you might have noticed, we do have vertical angles, which are always congruent no matter what. So, ooh, that's AAA though, right? That's not a way of proving triangles congruent if we have AAA. That's a way of proving triangles similar to each other. So I'm going to have to go with 2, but we can take a look at the rest. So for number 1, we would need a pair of congruent sides somewhere, either after the angles or in between the angles for either ASA or AAS. And I just don't see here any mention of the relationship between any of the sides here, any of the chords, or anything about the arcs that could help us figure that out. For number 3, angle ACB congruent to angle CBD. Well, that's not true. We already marked that angle C is congruent to angle D and angle A is congruent to angle B. This one is not congruent to this one. We marked them with different colors with different markings. And CA, arc CA, congruent to arc DB. So I don't know that for sure. If we knew that these sides were congruent, then that would for sure be true because congruent chords intercept congruent arcs. But since we couldn't conclude anything about the measurements of the chords or the relationships to each other, I can't say for sure that number 4 is true. Okay, in number 7, we are given the ratio of the arcs in the circle. So it's 5 to 2 to 1 to 7. So you can represent them as 5x, 2x, 1x, and 7x. So that means DF is 5x. So DF, let me try to mark that as best as I can. DF is 5x. FE would be the 2x part of the ratio. EG is the x part of the ratio, and GD from G to D is the 7x part of the ratio. Oops, I think I marked this incorrectly. So let's start again to make sure that we got it right. Okay, so let's start with the 5x part of the ratio, DF. I was going the wrong way. DF is right over here. So if it's not only named with 2 letters, we assume that it's the shorter arc. So 5x, my fault, I marked that one incorrectly. Okay, 2x, that's FE from here to here, 2x. Okay, then we have x, that's EG. And then we have 7x, and that's GD, that's this right over here. So I can make an equation to find x, plug it in, and then we can kind of figure out from there what the question's asking. So let me find a spot for my equation. 7x plus 5x plus 2x plus x is equal to 360 degrees because the whole circumference of a circle is 360. Let me really quickly combine my like terms using my calculator. I have 7x plus 5x plus 2x plus x, and I got 15x is equal to 360. So all we're going to do is 360 divided by 15, and we got x is equal to 24. Now I can just plug in to figure out what the arc measurements are. This arc over here, if I plug in, 24 times 5 is 120. 24 times 2 is 48 degrees. This is just 24 degrees over here. And 24 times 7, 24 times 7 is 168 degrees. Okay. What we need to do here is we need to identify one pair of inscribed angles that are congruent to each other and give their measurement. So let's check out inscribed angles that we have here. Let me get a different color for this. So here's an inscribed angle, angle FDE over here. And I know that it's half of its intercepted arc, which is 48. So that would make this inscribed angle over here 24 degrees. I see another inscribed angle over here, angle FGE. And once again, half of its intercepted arc, and it has the same intercepted arc, FE, which is 48 degrees. So that would be 24 as well. So I have answered the question. Angle FDE is congruent to angle FGE, and the measure of them both are 24 degrees. For number 8, it says in the diagram below of circle O, OB and OC are radii, and chords AB, BC, and AC are drawn. And we need to figure out which statement must always be true. So the first one's asking if angle BAC, this one right over here, is always congruent to angle BOC. Well, I'm already thinking that's not true, and let me tell you why. So the first angle, angle BAC, is an inscribed angle. It has its vertex on the circle, and it's opening up, it's intercepting arc BC over here. So it's half of arc BC. Oh no, I'm a bad highlighter. So it's half of arc BC. The other angle, angle BOC, is a central angle. Its vertex is on the center. So it's equal to the arc it's opening up to, which is also BC. So like if BC was 60, this would be 60, but this one would be 30. BC was 100, this one would be 100, but this one would be 50. So that's not true. These angles are not the same. One is equal to the arc and one is half of the arc. So I'm going to erase the markings on the diagram so we don't get confused here. And then I'm going to move on to the next answer choice. The next one's asking if angle BAC, so the one right over here, is equal to half of the measure of angle BOC. Well, we just talked about that, and that's true. We just said how this one's inscribed and this one's central, and they're opening up to the same arc. So if this arc was 60, this one would also be 60, but this one would be 30. If then this one was 100, this would also be 100, and this one would be 50. So regardless of what the arc is, whatever, this would always be the same as the arc, and this one would always be half of it. So that relationship is true. Let's talk about why the other two are not true. Triangle BAC and triangle BOC are isosceles. So OB and OC are radii of the circles. So it is true that triangle BOC is isosceles. But I don't know if triangle BAC is isosceles because AB is just a chord. It doesn't pass through the center. And AC is a chord. It doesn't pass through the center. So, I mean, it would be true if we knew that these arcs were congruent because chords that intercept congruent arcs are congruent. But since I don't know that, I can't draw the conclusion that AB is congruent to AC to say that triangle BAC is also isosceles. So I'm going to cross that one off. The area of triangle BAC is twice the area of triangle BOC. Well, area of a triangle is 1/2 base times height. I don't know what the base and the height are here. I'm not given any measurements. All I know are angle measurements here. And I do know this, all I know is angle relationships, not even measurements. Sorry about that. Angle relationships. The only thing here, based on what they give me that I know, is that this angle is half of this one, and this angle is half of this arc. This angle is equal to this arc, and that's all I know here. So I can't draw that conclusion. In the accompanying diagram of circle O, diameter AB is perpendicular to CD, and CD is a chord. So automatically, I see that the theorem applies that says if a diameter is perpendicular to a chord in a circle, the chord is bisected by the diameter. And since CD is 7, that means each half is 14. That means each half is going to be 7. So we just found that CE is going to be 7. For number 10, it says to answer the questions using the diagram given. For A, it says explain why arc AD is congruent to arc BE. So here's arc AD and here's arc BE. So notice that we're given the measurement of chord AD and chord EB, and we're told that they're both 5. So those are congruent to each other. And remember, we have a theorem that says congruent chords intercept congruent arcs. So chord AD is, its endpoints are A and D, so it's intercepting arc AD, and the chord that's congruent to AD, EB, its endpoints are E and B, so it's intercepting arc EB. So remember, congruent chords intercept congruent arcs, and that's why. I'll write that down. Congruent chords intercept congruent arcs. Since chord AD and chord EB are congruent, they both measure 5, the arcs that they intercept, which are arc AD and arc EB, will also be congruent. Then it says to find the value of x. Well, now that we know these arcs are congruent, we can set up and solve an equation. 5x minus 40 is equal to 10x plus 10. Let's solve this really quick. Subtract 10x on both sides. I get 5x. And add 40 to both sides. 5x is equal to 50. So I get x is equal to 50 divided by 5 is 10. Okay, now it's asking us to actually find arc AD and arc BE, so let's plug in. Let me get my calculator. 15 times 10 minus 40, that's 110 degrees for arc AD. And for arc EB, that's 10 times 10 plus 10. And that's 110 degrees. And it makes sense because we already said these arcs should end up being congruent. And when we plugged in our x value, we found that they are both congruent. They're both 110 degrees. Now it's asking us to find arc BD. Well, we know all the other arcs now. And the whole circumference of a circle is 360 degrees. So let me add 110, 110, and 40. And I'm just going to subtract that from 360. And I got 100 degrees for this arc over here. For number 11, it says points A, B, C, and D are located on circle O, forming trapezoid ABCD with AB parallel to DC. Which statement must be true? Let me draw a picture. So here's a circle. Oops, big circle. Let me move it over. And it says points A, B, C, and D are located on circle O, forming trapezoid ABCD with AB parallel to DC. So, and oops, let me try to do that a little bit better. It's because I didn't fully make this line segment here. So here we go. That will be AB. And this one here will be DC. And it's a trapezoid. So let me connect these. That doesn't really look like a trapezoid. Why don't I get my trapezoid bed in here instead of ones? Okay, that looks much better. I used my trapezoid bed in here. I'm a terrible artist. And let me label. So we have A, B, D, C. And I know that AB and DC are the parallel sides of the trapezoid. And it says which statement must be true. So I do know that parallel chords intercept congruent arcs. So AB and DC are parallel chords in the circle. So the arcs in between them would be arcs AD and arcs BC. So those are congruent to each other. Is that an answer choice? Oh, it is. Yay, I'm going to pick that one because I know for sure that's true. We have that parallel chords intercept congruent arcs. That is a theorem that we have. We can take a look at why the other ones are not true. So number one is not true because parallel does not mean that they're congruent. So if the arcs DC and AB were congruent, then we would know AB and DC were congruent because parallel chords intercept congruent congruent chords intercept congruent arcs. But we don't know anything about these two arcs, and we don't know that AB and DC are congruent. They don't tell us that. Parallel is not the same thing as congruent. That does not have to be true. It could be, but it doesn't have to be. Angle A is congruent to angle D. So angle D is an inscribed angle and it's opening up. Let me get a different color here so I can show this. So angle A, and then we'll do angle D. Angle A is an inscribed angle and it's opening up to arc, let me draw this, arc DCB. And angle D is also an inscribed angle. Let me get a different color for this one. And angle D is opening up to our ABC. So they both have BC in common. So that would be the same. But once again, we don't know anything about arc AB and arc DC and their relationship. So this would only be true if arc AB and arc DC had the same measurements, because then both of the intercepted arcs would be congruent. So the inscribed angles would both be half of them and be the same. But since we don't know anything about AB and DC, we can't really draw that conclusion. Once again, might be true, but we don't know that for sure. And finally, arc AB congruent to arc DC. Well, we've just been saying that we have no reason to know that arc AB and arc DC are congruent to each other. Might be true, but it doesn't have to be. If we did know that, then everything else here would be true as well. Okay, number 12. The pendulum of a clock swings through an angle of 2.5 radians as its tip travels through an arc of 50 centimeters. Find the length of the pendulum in centimeters. So we're finding arc length because when a pendulum of a clock is swinging, it's like making a circle. It's swinging around in like a circular motion. So since I'm given my angle in radians here for arc length, I'm just going to use the formula S equals R times theta because it's going to be a lot quicker. So S is arc length, that's what we're trying to find. Radius, oops, I misread the question, and that's why it's a good idea to always draw a diagram. So the pendulum is swinging around in a circular motion, and here's my pendulum of the clock swinging around and around and around, and it's going around and around, around in a circular manner. So we're told that the angle is 2.5 radians, and its tip, so the tip of the pendulum, which would be like here or here as it's going around, or somewhere else on the circle as it's moving around, travels through an arc of 50 centimeters. So it's actually giving us the arc length. And since we're finding the length of the pendulum, we're actually finding the radius. Because if the pendulum is on the clock, on the center of the clock, and it's swinging around and around and around and around, where it's swinging around in that circular manner is going to be the radius, whether it's here or here. Those are both the radius or somewhere else in the circle. So we're actually finding the radius. So that's important to make sure we're plugging in the correct things into this formula. So our arc length is 50 centimeters. We're finding our radius, and our angle is 2.5 radians. So to get the r by itself, all I'm going to do is divide both sides by 2.5, and r is equal to, let me get my calculator. I need 50 divided by 2.5, and I got 20. R is equal to 20. So the length of the pendulum is 20 centimeters. For number 13, it says in the diagram below, two concentric circles. So that means that they're two circles that are different sizes, but they both have the same center. As you can see here, they're overlapping and their centers are both at O here. And radii OC, OD, I'm guessing that means OCE, not OG, and ODF are drawn. If OC is 4, let me label this, and OE is 6, which relationship between the length of arc EF and the length of arc CD is always true? Well, why don't we test it out to kind of see? Because sometimes if I can't like figure it out just from looking at the answer choices, I like to test out the situation and see like what would actually be true. So let's say we know the radius here. So let's say that the central angle is like 60 degrees. I'm like making something up just so we can see an example. It doesn't tell us that there. So let me find the arc length of the smaller circle. I'm going to find the arc length of the bigger circle, and we'll see what the relationship is, and we'll see which is the correct answer choice for some random angle that I just made up here. So I'm using degrees, so I have to use a proportion here. Unless I just, no, I don't want to get into radians. It'll be easier with degrees to see the relationship. So we have arc length. Let me make my proportion here, arc length over circumference equals to central angle over 360 degrees. So first, let me do for the smaller circle. So we have arc length over circumference of the circle. The radius is 4. So the diameter would be 8. So that's 8 pi is equal to 60 degrees over 360. Cross multiplying that really, really quick on my calculator. Well, I have 360x is equal to, let me do 60 times 8. I got 480 pi, and dividing 480 by 360 and converting that to a fraction, I got that x is equal to 4/3 pi. Now I'm just going to do it for the bigger circle as well. So once again, arc length, I don't know, over circumference. Well, the radius of the bigger circle we know is 6. So the diameter would be 6 times 2, that's 12. So that would be 12 pi is equal to 60 degrees. That's the random angle I made up, over 360. Cross multiplying, we have 360x is equal to 60 times 12 is 720 pi. Dividing both sides by 360, I have that x is equal to 2 pi. So on my calculator, I'm just going to see 4/3 divided by 2. Okay, so 4/3 is about 1.3 repeating, and 2 is 2, so 2 is bigger. So on my calculator, and it should be bigger because that's from the bigger circle anyway. So I'm going to do bigger circle, which is 2. I can even type in pi if I want to, but I'm only really worried about the coefficients because pi is the same in both. So I'm just doing bigger over smaller. So 2 divided by 4/3. In your calculator, when you hit 2 divided by 4/3, put the 4/3 in parentheses anytime you're entering a fraction in. And when you hit enter, you should get 1.5. So I see here that the length of arc EF is 1.5 times the length of arc CD is the correct answer here. So we tested it out for one specific angle measurement. I just picked 60. You can pick any angle measurement. And you should see that given the radius measurements, the arc length should always be 1.5 times as big. You could have tried it with 30, 45, 10, 15, any angle measurement that you wanted to. Okay. Is this the last one? Nope, we got two more. So we're going to write a two-column proof of the following. Circle O with T is the midpoint of arc CH. So we know that midpoints cut arcs into two congruent pieces. And we're proving that CT over CH is equal to TO over TH. So we're proving a proportion, and we know that the step right before we prove a proportion is to prove two triangles similar. Now we're going to take a look at the proportion to figure out what triangles here we're proving similar. So CT is right here. CH is connected to CT. Oops, I'm a bad highlighter, as I said many times. And they're both from the big triangle. So the big triangle is one triangle that we're focusing on. TO is right here, and TH is connected to TO, so I'm going to use the same color for it. And they're both sides of that smaller triangle on the bottom. So we're trying to prove that the big red triangle is similar to the small green triangle. Now already I see that they share angle H. So I'm going to just mark that. Angle H is congruent to itself by the reflexive property. We're interested in angles, not sides, if we're proving triangles similar because we want AA, and I already have a pair of angles, so I just need one more pair of angles. So I'm also noticing that we have inscribed angles. Angle H is an inscribed angle, or I should say angle CHT, and it's opening up to arc CT. Angle C is also an inscribed angle, and as you can see, it's opening up to arc TH, which is congruent to arc CT. So since inscribed angles are half the measurement of their intercepted arcs, I see that those inscribed angles are congruent because inscribed angles that intercept the same arc or congruent arcs are also congruent. But the more I'm thinking about it, I don't think the inscribed angles are going to work because we already are using angle H, which I marked in the two triangles. I just drew them separately down here. Always a good idea whenever you're working with two overlapping triangles so you can see the parts of them clearly. So I also see that we have central angles here, so that might be a better option. O is the center of the circle. So I see this angle over here is opening up to this arc. And I see this central angle over here is opening up to this arc. Oops, I'm erasing too much. So what I'm actually going to do is, although this is true, both of these triangles do share this angle. I think it would be more useful to put down what we were talking about with the inscribed angles that were sharing the same arc. So once again, angle H is an inscribed angle that's opening up to arc CT, and angle C is an inscribed angle that's opening up to arc TH. Since these two arcs are congruent, we know that inscribed angles that intercept the same arc are also congruent. For example, if these are both 60, these are both 30. If these are both 90, these are both 45. So inscribed angles that intercept the same or congruent arcs are congruent to each other. So that's THC and OHT. There we go. Now, I noticed that angle T is also an inscribed angle, and it's opening up to arc CH, which is half a circle or a semicircle. So that's 180. And since this is an inscribed angle, it's half of its intercepted arc. So if its intercepted arc is 180, this is 90. So I know that we have a right angle here. I also know that these two arcs are congruent to each other, and together, these two arcs make a whole half a circle or 180 degrees. So each piece, since they're congruent, should be 90 degrees. And since angle TOH is a central angle, it's got its vertex on the center of the circle, it's congruent to its intercepted arc. So if its intercepted arc is 90, that means that we have a right angle over here as well. And now I have my two pairs of congruent angles for AA. Let's write this up in a proof. So let me make my statement, reason chart. So let me write this up. So my first step is my givens. I'm not going to write them all down now. Then we said that arc CT is congruent to arc HT, and our reason is that midpoints split arcs into two congruent parts. Any way of wording that says that this whole arc TH, is being split equally in half is totally fine. Okay, then we mentioned how angle TCH and angle THO, TCH and THO, are congruent to each other. And that's because inscribed angles that intercept congruent arcs are congruent. From there, we can then say that angle CTH, this angle here, is a 90-degree angle, a right angle, is a right angle. Now remember, that's because it was an inscribed angle that intercepted a half a circle, which was 180 degrees. So since inscribed angles are half of their intercepted arc, if this is half a circle or 180, the inscribed angle is 90. So I'm going to write inscribed angles that intercept semicircles, which are 180 degrees, are right angles. From here, all we need to mention is our other right angle, angle TOH. So I'm going to write that down over here. Before I can mention that this is a right angle, I do need to say that arc TH is 90 degrees. So I'm going to write that here. Arc TH is 90 degrees. And I will just write half of a semicircle is 90 degrees because the whole arc CH was a semicircle. And we knew from the midpoint earlier on that the arc was being cut in half into two equal parts. So half of the semicircle is 90 degrees. And then from there, I can say that angle TOH is a right angle. And our reason for that is that angle TOH is a central angle, and central angles are equal to their intercepted arcs. Central angles are congruent to their intercepted arcs. Let me get a little bit more space and continue my statement reason chart down here. So I do actually have to say that the two right angles are congruent to each other. So I'm going to say angle CTH, this one over here, and angle TOH, this one over here, are congruent to each other. And since they're both right angles, I can use the reason all right angles are congruent to each other. From there, I can say that the two triangles are similar. Triangle CTH is similar to triangle TOH, and my reason for that is AA. Now that I know the triangles are similar, I can end by proving my proportion. CT over CH is equal to TO over TH. And whenever you're proving a proportion, it's the same reason every time. Corresponding sides of similar triangles are in proportion. There we have it for this proof. Okay, next one, and this one's going to be quicker. We know here that AD is parallel to BC, and we are trying to prove that BE is congruent to CE. So whenever we're trying to prove that a pair of corresponding sides or angles are congruent, that tells me that we're going to be using Cpctc. So before that, we're going to have to prove triangles congruent to each other. So BE is part of, well, let me see also the other one is CE. Okay, so it appears like to me I'm going to be proving this triangle and this triangle congruent to each other, because then if we can prove these triangles congruent to each other, then we can prove BE congruent to CE because of Cpctc. They're corresponding parts of triangles that we are going to prove congruent to each other. So let's see what we know here. If we have parallel chords, they intercept congruent arcs. And that means that the chords are congruent as well, AB and CD, because congruent chords intercept congruent arcs. So that's a pair of sides already for us. I also see the vertical angles here, so that works. Now let's try to find either another pair of angles or another pair of sides here. So I think I can get another pair of angles here. I think I can get this angle and this angle over here. Notice how they're both inscribed angles. And really quickly, just to show you guys, this inscribed angle here is opening up, is opening up to arc CB. And also, this inscribed angle over here is also opening up to arc CB. So inscribed angles that intercept the same or congruent arcs are congruent to each other. So I'll erase that so it's more clear. And now it looks like we have angle, angle, side. So we can prove the triangle's congruent. After proving the triangle's congruent, it's one more step to use Cpctc. So let me make my statement reason chart. First step is the givens, but I'm going to skip those to make the video a bit shorter here. Okay. Then after our givens, we knew that arc AB was congruent to arc CD, and that was because parallel chords intercept congruent arcs. Then from there, we knew that AB, chord AB, was congruent to chord CD. And that's because congruent chords intercept congruent arcs. So we knew that these arcs were congruent, so the chords that intercepted them are also congruent. Then for our first pair of angles, we use the vertical angles. That's angle CEA congruent to angle BEA. And I'm going to write here vertical angles are always congruent. And then for our second pair of angles, we had angle BAE congruent to angle CDE. Those are the two angles in black. And that was because inscribed angles that intercept the same arc are congruent. From there, we know that the two triangles are congruent. So triangle BAE is congruent to triangle CDE, and that was by angle, angle, side. And after that, it's one more step to prove BE congruent to CE. And we're able to do that because we already proved the two triangles congruent. So any other pair of corresponding sides or corresponding angles is also congruent by Cpctc because we already proved the triangles congruent. And there we have it.